So far, we've been defining equilibria of extensive form games via their normalization. So that is, we define a Nash equilibrium of a normal form game to be a Nash equilibrium of its corresponding normal form. So in this video, we're going to define a new solution concept called subgame perfect equilibrium, which is actually aware of the structure of extensive form games. Subgame perfect equilibrium is what's called an equilibrium refinement of Nash, which is to say it's a specialization. So every subgame perfect equilibrium is going to be Nash, but there are going to be Nash equilibria which are not subgame perfect. So that is to say, it's ruling out certain Nash equilibria as bad. So I'm going to introduce this through an example, which is the ultimatum game. So in the last video, we worked out that the ultimatum game, which is this game, had 3 Nash equilibria. So one of these, which is probably the most interesting one, is player 1 plays F, which is the fair split, and player 2 accepts on the condition of a fair split and rejects if there was an unfair split. So what's happening here is that player 2 is making a threat, namely the threat that if player 1 played U, then player 2 will respond with R. So let's think about what's actually happening in this equilibrium. Player 1 is playing F, which, given player 2's strategy, leads to player 1 getting an outcome of 5, because we follow this path. If player 1 had hypothetically decided to play U, then according to player 2's strategy, we will end up here. And so player 1 will get a payoff of 0. So this is the reason why player 1 prefers F to U, because this payoff 5 is greater than this payoff 0. But if you think about it, supposing player 1 did actually play U, then player 2, by playing R, has got a payoff of 0, whereas if they accepted it, they could get a payoff of 2. So stop thinking about this in terms of fairness and start thinking about it just in terms of just optimization, players who want a higher payoff. If we were hypothetically here, player 2 should still prefer to get a payoff of 2 to a payoff of 0. So this threat to respond to U with R is what's called a non-credible threat. It is to say, it is a threat which would not actually be rational for the player to carry out. The reason that this is still a Nash equilibrium is that when we check the optimality conditions for a Nash equilibrium, we only check along the path of play, which is this node and this node. We never actually check what would happen if we ended up here. So subgame perfect equilibrium is all about kind of doing that, checking what happens at nodes which are off the path of play. Okay. So for any node in any extensive form game, we can ask the question, what would happen if we hypothetically reach this node, even if we can't actually reach it, and then continue playing from here? So what that means is, for any node in a game, we can take the subtree from that node, and we can consider that subtree as a game in its own, as an extensive form game in its own right. So we inherit all of the extra data that's attached to the tree. So we inherit the node ownership decorations, we inherit actions, we inherit payoffs, and then you get a well-defined extensive form game. So this is going to be called a subgame of the original game. So subgame comes from taking any node in the original game and then taking the subtree from that point. And in particular, any game is a subgame of itself because you can always take the root node. The subtree from the root node is just the tree that you started with. So we're going to say a proper subgame is any subgame other than the one that you get from the root node. Okay, it's also worth noting, if you have a strategy profile for any extensive form game, then you have you can restrict it to a strategy profile for any subgame of it, namely just by ignoring all the nodes that you've thrown out. So a strategy profile says what to do at every node, and then if you take a subtree, you know what to do in every node in that subtree. Okay, now here's the big definition. A strategy profile, I forgot to say, a pure strategy profile is going to be called a subgame perfect equilibrium if you restrict it to any subgame, including the whole game, it's going to be a Nash equilibrium on that subgame. So actually, there's a lot going on here. So to check this, in principle, what you would have to do is check for every possible subtree, you would have to take its normal form and then check whether you're a Nash equilibrium for that normal form. Trivially, every subgame perfect equilibrium is going to be a Nash equilibrium because it has to be a Nash equilibrium for every subgame, and every game is a subgame for itself. So in particular, it's going to be a Nash equilibrium for the whole game. But on the other hand, there can be Nash equilibria which are not subgame perfect, and the example that we saw a couple of slides ago is going to be an example of this. So Nash equilibria are going to be essentially optimal at every node along the path of play. And so the Nash equilibria which are not subgame perfect are going to be things which are optimal along the path of play, but fail to be optimal somewhere else. So the idea is that this subgame perfect equilibrium is going to be a strengthening of Nash that's going to rule out non-credible threats. Okay, so if you remember, for the ultimatum game, we have 3 Nash equilibria. And it's going to turn out that, so FAR, which is the one we were talking about before, is not a subgame perfect equilibrium, because if you restrict it to this subgame, taking from this node here, it fails to be a Nash equilibrium. So the subgame from here is in fact a 1-player game consisting only of player 2, where if they choose A, they will get a payoff of 2, and if they choose R, they will get a payoff of 0. And if you restrict this strategy profile to that subgame, the strategy says player 2 plays R, and clearly playing R is not an Nash equilibrium because 2 is greater than 0. Similarly, we have this strategy profile URA, and this is a kind of obviously silly strategy profile, so this also turns out to be an Nash equilibrium, but it doesn't really make sense. So this is player 1 makes a threat to reject a fair offer, but will accept an unfair offer, and so that's forcing player 1 to play an unfair offer. So this doesn't make sense, but it turns out that it is Nash. Essentially because for the same reason, but here it's kind of more intuitively obvious that it's silly. But we have to check what happens on this node, which we don't reach along the path of play, to see that rejecting is worse than accepting. So this is not subgame perfect because it fails to be Nash on this subgame, although it is Nash here and here. So this leaves us with this Nash equilibrium where player 1 plays an unfair offer and player 2 unconditionally will accept either a fair or an unfair offer. And this turns out to be the unique subgame perfect equilibrium. So notice that this is sort of a bad equilibrium because FAR is the one where the fair split is actually reached, but we've ruled that one out using subgame perfect equilibrium, and we've been left with a unique subgame perfect equilibrium, which is a kind of non-fair outcome. Okay, just like for Nash, we had a kind of a procedure to check it, which doesn't involve computing the normal form. Namely, we check an optimality condition and every node along the path of play. We can do a similar thing for subgame perfect equilibrium, except we have to check every node. So this is a little bit more complicated. So what we're going to do is that for every node so given a strategy profile, a pure strategy profile, given every node and every outgoing edge of that node, we're going to assign a real number to it, which is going to be the payoff that the player owning this node will get if they follow that action, but everywhere subsequently from there, they follow the strategy, everybody follows the strategy profile. So this is a one-shot deviation. Notice we're going to do this at every node, including nodes that we can't actually reach by following the strategy profile. So this is called a one-shot deviation. And it's going to turn out that our strategy profile is a subgame perfect equilibrium exactly when, for every node, the action that the strategy says to do is the one that results in the highest number among all of the actions at that node. So this turns out to be equivalent to the condition for checking Nash, except that for Nash, we're only going to check along the nodes that we reach along the path of play, whereas here we're going to have to check this condition at every node. But doing this is a lot less work than computing the normal form of every single subgame.